Hello everyone. So today I will be giving a demo on RCNN using PyTorch. So RCNN is an object detection algorithm where given an image we have to find object's position and classify detected objects into different categories. So here is an example where given an image we have to find what are the different objects present in this image. So in object detection we are trying to solve two tasks. One is object localization and another is classification. In object localization, we are finding different bounding boxes present in the images. So we are localizing where are different objects present in an image, and in classification, we are classifying categories of objects present inside this bounding box. So object detection research has been evolving from past 3 decades, and evolution of these methods happens in different phases, which we can divide into two categories. One is traditional object detection methods, and another is deep learning based object detection. Our main focus in this demo is in deep learning based object detection method. Traditional object detection methods used handcrafted features or traditional computer vision algorithms to extract features. These features include shift or hop. I will provide more resources if you want to go deep into these traditional methods. So this Voila Jones detector is also currently being used in many cameras for detecting faces. It works very well with faces and in real time also. It works very well with faces because faces have a similar geometry, and in most images the faces are in same orientation, which is upright direction. So another method, hog detector. Hog detector is a sliding window technique where we slide a window across an image, and while sliding we calculate hog features, which is a traditional computer vision feature extractor method, and then we use those features to train a SVM and detect what is the category inside that window. DPM uses DPM uses hog features and apply those hog features on different parts of images and then merge these parts for output. So since our main focus is deep learning based object detection method, and we will move towards that. So these deep learning based object detection methods are further categorized into two categories. One is two-stage detector and another is single-stage detector. Two-stage detector uses two-stage pipeline where first we have to extract bounding boxes and then use those bounding boxes to classify the images inside those bounding boxes. Another is single-stage detector methods where we in one forward pass we are finding all the different bounding boxes as well as categorizing those bounding boxes in one pass. That's why you have seen methods like you only look once, YOLO methods quite very popular in object detection tool. Today we will be only focusing on RCNN based method, which is Region Convolutional Neural Network, and it is given by um, R. Girsi in 2004. So first we will start with installing and importing dependencies. We will be using Kaggle to download a pre-processed dataset for RCNN. Then we will import the required dependencies. We will be using PyTorch, OpenCV, Pickle for loading and saving pre-processed data, and then Torch NN, Torch Optim for creating and training neural networks. Then we will be also using Torch Vision for creating dataset, Pascal VOC dataset, as well as downloading ResNet 50 pretrained backbone. And we will be also using matplotlib.pyplot for plotting things. So first we will be loading and exploring a data bit. So here we are using Torch Vision.datasets to load the Pascal VOC dataset. So here we have loaded trained dataset as well as test dataset. Let's print a sample from the dataset. We can see that this dataset contains tuple. So that in this tuple we have two things. One is image, which is a pillow image, and another is annotation of this image. So this pillow image can be converted into NumPy array using np.array. and then we will get a numpy array of this image. And this annotation contains a lot of information about the image, but the most important information that we will require in this demo is this object information, which is a list, and inside this list we have dictionaries. The information which we require are name and the bounding box information. So name is the label of that object and bounding box is the location of that object. To describe a location of an object, we require 4 coordinates. So 2 coordinates will define the top left part of the bounding box, and these 2 coordinates will define the bottom right part of the bounding box. And using these two points, x min, y min, and x max, y max, we can plot boxes. Now, if we see that our image consists of height 333, width 500, and it has 3 segments, since it is a RGB image. Now we will be looking at all the unique object classes present in the data set. For this, we have created an empty list, and we are iterating over our data set, and we are getting the information of annotation object. So this is our whole. First, we will be extracting this part using index 1, and then inside this we will be getting annotation, and this annotation is a dictionary. And inside this dictionary we want object information, which is present here. And this object information is a list. So we are iterating over that list, and we are getting the name key from that dictionary, and we are appending it to our all object data. Then we are using set to convert this list into set object, and then this set will contain the unique class. Then we are calculating the length of this set, as well as we are printing those unique labels. So as we can see, our data set consists of 20 unique labels, and these are the label categories present in our data set. So this data set consists of things like dog, dining table, potted plant, dog, horse, person, goat, sheep, car, sofa, etc. You can look through the list yourself. Next, we will define 2 dictionaries. One dictionary will map string labels into index, and another will map index into label. So to pass things into neural network, we have to convert strings into numbers. So this dictionary will map those things. And while plotting, we will require inverse process, where given a index, we want to get which label this index corresponds. For that, we will use index to label dictionary. Next, we have defined a helper function called draw boxes. So this draw boxes takes image as NP array and the number of boxes present in this image. So this image might contain multiple boxes, and for each boxes we require 4 coordinates. Then labels means label present in the bounding boxes. So the label can be car, dog, etc. And scores are the probabilities that given object is present in the bounding box. That is with how much probability that for example dog is present in this box. And next is class map. And class map is a dictionary that maps index to class names. So in our case, this IDX2 label dictionary can be a class map. Now to plot things, we are first finding the length of the boxes. Then we are iterating over till that length. And then we are extracting those coordinates for the boxes. So we will extract x min, y min for each object, and x max, y max for each object. And these 2 coordinates are referred as x1, y1 and x2, y2 here. And then we will use cv2 rectangle function and pass our image as well as the box coordinates, and then which color we want our box to be, and and the width. Next, we then convert our label into text if class map is provided. Then we are just using CV to put text to enter the label as well as the score in above the rectangle. So here is an example of this draw function. We are just taking one sample from the data set, converting it into an array, extracting our annotation information, and then getting all the boxes and getting all the labels from the data set for that image. And then we are using one as a score currently because we already know that this is car since it is true label. Then we are drawing the boxes. So as we can see that this red bounding box is around this car object, and car is written on top of that box with probability 1. So this draw function will return an image with bounding box and label as well as probability written on top of the box. Next, we have to define calculate IOU score. Calculate IOU score function takes two things, box 1 and box 2. So it takes two boxes and calculate IOU score between these two boxes. So IOU score is area of overlap between two boxes and divided by area of union of both boxes. So consider this outer box as an image. So this image is of dimension 224 cross 224. So the topmost coordinate is 0, 0 and the bottommost coordinate is 224, 224. Now consider two boxes, box A and box B. Box A is defined by two coordinates x1a, y1a, x2a, y2a, and box 2 is defined by these two coordinates x1b, y1b, x2b, y2b. To find the intersection rectangle, we have to find these two coordinates, this coordinate as well as this coordinate. So this coordinate can be found as maximum of x1a, x1b. So here. So in this case, we can see that x1b is maximum. Therefore, this coordinate will have one point x1, x1b, and another point will be maximum of y1a, y1b. So y1a is maximum. Therefore, for this point we have point x1, x1b, y1a. Similarly, now for this point, we will use this formulation, and from this we get x2a, y2b. So now we have defined these two coordinates using this formulation. We get the coordinates of this intersection bounding box. Now we have done the same thing here. We have first find the intersection bounding box points by finding the maximum of box 1 x1 and box 2 x1 and box 1 y1 and box 2 y1. Then for the rightmost coordinate we have find the minimum. Then to calculate the area, we know the area of a rectangle is length into breadth. So we are just doing that here in this point. Then to calculate the area of box 1, we are using similar formula, length into breadth for the box 1 and then length into breadth for the box 2. Then to find area of union, we are using a formula from set theory, which is a union B equals to A plus B minus A intersection B. So we are using that same formula here, and then we are getting the area of union. Then to calculate the IOU score, what we have to do, we have to just divide area of intersection upon area of union, which we are doing here, and we are getting IOU score. Now coming to RCNN paper, so this is a picture from the paper itself. So So in RCNN, we are given an input image. Then we first have to find we first have to find all the box proposals here. So we use selective search algorithm for generating region proposals by merging similar pixels into regions. So a selective search algorithm was given by Islings et al. And it works in steps. So in first step, we generate initial sub segmentation using methods like graph-based image segmentation, and then apply greedy algorithm to combine similar regions into larger region. Then use those regions to produce candidate object locations. So these selective search algorithm is not related to deep learning. It is a traditional computer vision based algorithm, and I will provide more links for that because it contains some graph based image segmentation methods. We will be directly using this selective search algorithm from OpenCV package. Provide you some resources, and you can look more into this selective search algorithm. Then after we get the proposed bounding boxes, we will take those bounding boxes and warp those bounding boxes into a fixed size images, and then pass it to neural network, and then it will predict whether it is a aeroplane, car, person, or TV meter, etc. That is, it will classify these regions proposed by the first selective search algorithm. So this method is efficient than previous methods because, like, if you check the Hawk paper, it uses sliding window proposal. So what we do in that method is that we take a window, and then we pass it to our classifier, and then it classifies this region. Then we slide our window again with some stride value, and then again send it to classifier. Similar, this way we slide window over the whole image and send it to classifier and classify each and every page based on that sliding window. So this method was very inefficient. So this selective search algorithm is more efficient because it first searches the possible objects inside the image, and then we only pass some sections of the image, not the whole possible combinations from that. So steps to train RCNN. We first apply selective search algorithm to find box proposals. Then we take those boxes in the dataset whose IOE score is greater than some threshold. Since we already have true boxes, we will calculate IOE score between the proposed boxes by selective search algorithm and the true boxes. And if they are greater than some threshold value, we will take those boxes for our label. We also save some boxes which contains no object and label them as 0, which is background, so that our model also knows information about background. So we then train a CNN based model in the prepared dataset. So steps for inference is like we first apply selective search algorithm to the image, then pass all the proposed boxes to train CNN model, and then we get using the above. So to do inference with RCNN, we first apply selective search algorithm to per image, then pass all the proposed bounding boxes to the trained CNN that we get from the above step, and then we will do some post processing to remove some of the unnecessary boxes. We will use algorithm like non-net suppression, and we will look on this algorithm later. Now we are creating dataset for the training. So dataset so we will be creating dataset using selective search algorithm. So here we have created two lists. One is true class list, and another is image sections list. And then we are also initializing two counters with zeros, true count and false count. Then we are first getting the label from our dataset. We are also getting the bounding box from the dataset, and we are getting the image from the dataset. Then then what we are doing is we are this rex contains all the proposed bounding boxes which are extracted using selective search algorithm. So our these yellow boxes are inside this rex. So we will loop through all these recs, and we will calculate IOU score between the proposed bounding box, which is bounding box, which is this rec, as well as our true bounding box, which is this box, which we get from the dataset. And we check if our IOU score is greater than some threshold. We have we can set this IOU threshold to 0.5 or 0.6 based on this is kind of a hyperparameter which we can tune. And if our true count is less than some number of max boxes, so we can set some max boxes here. For example, we want only 10 boxes or 100 boxes, we can set that here. If our true count is less than max boxes, then we will append this label to our into our true classes list. Then we will also extract that the portion of the image from this rectangle location, and then set it and then save it into append it into image sections. Similarly, we will also save some of the background images. So for that, similarly, we are setting some max number of boxes for background images also, and we are saving true label as 0, which is background image, and then we are saving that portion into image sections. Then we are returning the image sections and true labels list. To creating this data set for RCNN takes some time. We have created a preprocessed version of data set for RCNN training and provided it through Kaggle dataset. This data set is approx 5 GB. So to create an API file, you first have to go to your Kaggle account and scroll to the API section. And in that API section, you have to click on create new tool. So steps have been included in this notebook, and you can go through this. Next, here we have defined some things. Max IOU threshold of 0.7, and we want 50 boxes from each set of images, and we are also restricting 1000 boxes which from the selective search algorithm. Then we have defined paths for saving or trainer validation patches that we will get from this process data for RCNN function. And now we are creating our data set here for training and validation using the above process function. So here we have applied selective search algorithm. We are using cv2.img proc segmentation for selective search segmentation. Then we have switched to fast version of this algorithm, and then we are getting all the rectangles using sh.process. These rectangles are of form x, y, width and height of that rectangle. X, y are the top left coordinates, and w and h are width and height of the box. To convert in our format, we have to because since we already have top left coordinates, we want bottom right coordinates. To get bottom right coordinates, we are just adding the x with the width of image and y with the height of image. Then we are calling this process data for RCNN function and getting all the images and classes from this after the processing. Then we are just adding it into this all images and all labels list. Then we are saving all those information and label information into a pickle file. So if data is already processed, for example, if you are downloading it from the Kaggle link we have provided and following these steps for loading the data set, then this step will not run because data set is already processed. Similarly, we are doing it for validation. validation dataset. Now we are creating PyTorch dataset. For that, we will be inheriting torch.utils.data.dataset class, and we will create a dataset using this. So we have defined our constructor here. This constructor takes preprocessed data folder as well as section dimension. So after this proposed box is given, we have to reshape it to some dimension, which we have set 224 by 224 in this example. We also want to normalize this image because we will be using pre-trained backbone, ResNet pre-trained backbone, and it requires our inputs to be normalized. We have now defined a get item function. So what we do is we get index as input in the get item function, and we first load pickle file. We first load a pickle file that we have saved in that index, and then we get our data and label. Then we resize our image with this 224 cross 224 dimension, and we are also then we are converting our label as well as image into torch.tensor. Next, we have defined imshow function to visualize the batches of data. So you can check this function for plotting. Next, we are defining our RCNN dataset, and we are passing those folders for preprocessed data save train and preprocessed data save well. And we are defining the section dimension as 224 cross 224. Now we can check the statistics of data. Our one sample consists of shape 3, 224, 220. Then we have this image type of float 32, and our label is of type int64, and total number of samples we have in our dataset is 80,270. Similarly, we have printed the statistics for validation dataset. Now we are creating data loader here for training and training and validation dataset. We are using 32 batch size for training and 64 batch size for validation, and we have added shuffle equals to 2 for training and false for validation. Now here we have plotted a grid of images using the above imshow function that we have shown. So these are some of the images from the dataset. We can see that this is one of the proposal from an image, and it consists of a person. This consists of C. This is a background image. This bounding box contains person. This contains bird. So these are some background images. This is bicycle image. So this contains this dataset contains now images with classes and classes that are present in VOC dataset, as well as one extra class which is for background images. Similarly, we have plotted for our validation dataset. You can check that. Now we are defining our device. So if we are using GPU, then we will be using CUDA. So now we will define our model. So our build model function takes two parameters, backbone and num classes. So backbone in our case, backbone will be a simple ResNet model, which is a CNN based network. We will pass image into that network, and we will get features from that model. These features can then be passed to a classifier, which we have defined here. So our classifier is using dropout and linear layers and two sets of linear layers, and and in the final layer our number of neurons will be num classes plus 1. Num classes are 20 and 1 for background, which is overall we have 21 output neurons in our output. Now here we have defined our ResNet backbone. We will be using torch vision models .ResNet 50 to download a pre-trained checkpoints of this ResNet 50 trained on ImageNet dataset. Then to save our time for training, we are just freezing the pre-trained model using by setting the gradients required grades to false for each parameter in the model. Then we are then we are giving this backbone to our build model function, and then it is returning model. This is our model. Our model is a ResNet model, ResNet 50 model with with feature extractor T layer, and then these are our classifier layers. We will train only these layers. Other layers are freezed in the above step. Now here we are defining class weights. So these class weights, in class weights we are giving more weightage to non-background classes because the number of non-background classes is less than the background classes. Then we have defined a cross entropy loss and passing those weights those weights tensor into our weight parameter. Then we are defining our optimizer. Here we will be using Adam optimizer with learning rate of 1 in 1. This is usual code for training the model. It is similar to image classification model that we have previously seen on lot of the demos. So I will go through it very quickly. So here we are going through some number of epochs, and in each epoch in each epoch we will get the batch of images and labels. We will pass those images and labels to the GPU device. We will then make prediction using those images, and then we will calculate loss between our prediction and our labels, and then we will do back propagation and update the parameters. For similarly, here we are doing validation steps. You can check more. We have already gone through this code a lot of time in previous demos, so I am not going through that. So when we run this cell, we will be training our model. We can see that our train loss and validation loss here, and train accuracy and validation rate. So we can check that our train loss is decreasing, our train accuracy increases. So now after model is trained, we have to do inference from that. So to do inference, we will be preparing the images similar to like we have prepared it for training. So we will be normalizing our images. Then we have defined a process inputs function that takes images at input and then makes selections and section sizes, other parameters. Then we will apply select to search algorithm on that images and pass all the proposed boxes and pass all the proposed boxes as well as our image section on those boxes. So now we can check that. Here we are loading our best model checkpoints, and then we are loading our validation image. Then we are processing our validation image. So we have defined this process input function above as we have seen already, and we are passing our validation image into this, and this function will return two things. One is the sections of each image on the proposed bounding box and all the proposed bounding box. So we can check the shape of our validation images and boxes here. You can see that we have 300 images with size of 224 cross 224, and we have similarly 300 boxes for each image. Now we are setting our model into eval mode, and then passing those prepared validation images into our model, and then getting the scores for each class for each image. Then we are getting the scores for each image. Then we have defined a function called process outputs that will process the that will take scores validation boxes, and threshold IOU threshold as input, and then preprocess those boxes. So now let's check our process outputs function. This process outputs function first takes argmax along the axis 1 in the scores and find the labels. Then we are also finding the maximum probability of that object, and then we are checking if all the index we are saving all the indexes where labels is not equal to 0. That is, those labels contain some objects. It is not background image. Then we get all those boxes, probabilities, and labels from those indexes. Then we will pass those three things along with the threshold and IU threshold to our non-maximal max suppression algorithm, and this will pre-process our boxes, and then it will return all the final boxes, final scores, and final labels. Now we will look into this non-max suppression algorithm. Non-max suppression is a computer vision method that selects a single bounding box from many overlapping bounding boxes in object detection. The criteria is usually discarding entities that are below a given probability threshold. So to explain this, I will go to the whiteboard. So now let's see non-max suppression algorithm with an example. So here we have three boxes for a single object. So consider that object is dog. So for dog, our model has given three boxes: box A, box B, and box C. Box A has probability 0.9 of having dog inside it. Box B has probability 0.5 of having dog inside it, and box C has probability 0.6 of having dog inside it. Now we will first sort our boxes in some particular order. We have choose ascending order here. So B box will come first, then C box come, then A box come. Then we choose the box with highest probability, which is box A, that is in the last. We will choose that box and compare with the other boxes. So while comparing, we will first check if these two boxes correspond to same classes or not. Since these three boxes correspond to dog, so A and C can be compared, and A and B can also be compared. So we will compare IOU score between these two boxes, and if it is greater than 0.5, we will neglect the C. So consider, for example, here we assume that box C has IOU score of less than 0.5. So we will not remove that. Then we will compare A with B. Now we will calculate IOU score between A and B, and let us assume that it is greater than 0.5. Then we will discard that box from our prediction. So it will be removed. So we only left with two boxes. Then we will keep aside this. Then we will keep aside this A box from here. So A box, we will prepare another list called as chosen boxes, and we will enter A in that box. Now we have and B is already removed from our list. So now we only have one box remaining in our sorted order list, which is C box. So since we cannot compare it with any other, we will just move this box to our chosen box list. So now we have two boxes after post processing, after applying non-max suppression algorithm. So if we choose a threshold of something like 0.4, this box might have also been removed, and we would have gotten a only single bounding box for our dog. So so now coming back to the code, this threshold is the probability that we are looking at. If the box contains probability is greater than 0.5, we will only consider those boxes. And the IOU threshold is the same that we have seen before. If the threshold between chosen box and the current box is greater than some IOU threshold, we will neglect those boxes. So, like in our case, we have neglected box B based on IOU threshold of 0.5. Now this algorithm works similar to this. We will first sort the boxes based on the score. Then we will get our last index here, similar to which we have already explained. Then we have appended that last index box into a chosen box list. Now we are looking through all the boxes, and our current box is at index IDX. In in this section, we are first checking if our chosen box label is equal to current box label, and we are calculating IOU score between current box and chosen box, and checking if it is greater than some IOU threshold. If that's the case, then we are just deleting that box, and finally we are returning all our final boxes. Now after processing, we will use our draw function above we have defined, and we have plotted this output here. You can see that for some things like chair, it has detected very well, but for that there is no potted plant, but it is detecting that potted plant. There is no TV monitor, but it is detecting here. So you can refine, you can play with these IU threshold values and threshold values more to refine these boxes more better. Here we have defined predict function using this same idea. Here we are first preparing our boxes, then we are passing those sectioned images into our model, then getting the classification scores, and then passing those boxes and classification score into process output function that will use maximum suppression algorithm in the backend, and then we will return our boxes and labels. Now here we are plotting some images with the model's prediction, so you can look into those predictions. So here you can check that like the horse is correctly defined, this person is also been extracted here. Here also like this cat there are two cats, but you can see there are a lot more boxes, so it needs more bit processing. Like here person is correctly classified, detected and classified. So the next exercise can be how can you pre-process these outputs more better. So you can check on those things. Thank you.